Okay, so today we're looking at force versus time graphs again, page 283 from the textbook. We will determine the impulse and the area under a force time graph, include constant positive and negative force, uniformly changing force. We did in grade 11, we looked at velocity time graphs, right? And the area under a velocity time graph is the what? The displacement, right? Because you know that the formula, d equals v times t, right? You know that right from probably grade 9 or grade 10 kind of thing. If the graph itself, the velocity time graph is like this, a flat one, constant velocity, well then velocity multiplied by time is distance. And in a graphical sense, velocity multiplied by time is length times width. It's the area of that rectangle, right? That's the concept. So the same thing on a force versus time graph, because impulse is force multiplied by time. If you have a force like this, the area, if it had a constant force, the force multiplied by the time is a rectangle, and you get area. So that's why area under a force versus time graph is the impulse. What's flashing at me here? Okay, well, that's kind of, I basically gave you the entire lesson sort of in preview format there. So if a constant force acts over time, the basic graph will look like this, right? You guys have this on that handout? The one with the boxes around it? Okay. So what is the area under the graph? Force multiplied by time is the fill in the blank thing. It's like back to grade 9 where you fill in the blanks on the notes. Force times time is the area under the graph. And we know that impulse is defined as force multiplied by time. Therefore, the area under the graph is defined as the impulse. So this area here is impulse J. Okay? That's when a constant force acts over a period of time. Right? You push an object with a certain force over a period of time, a constant force. You've got that pulley setup that we did when we did frictional coefficients, right? And you've got gravitational force pulling over a pulley. It's a constant force over a time, right? That's the impulse. Now, most of the time, most of the cases, force is not constant, right? When you hit a baseball with a bat or a tennis ball with a racket, in most cases, force is not constant and increases as colliding objects are compressed, and as they move away from each other, they actually decrease, right? So quite often in real life, you're going to get a force versus time graph that looks sort of like this one here. And you guys should have that on page 2 of that student handout. Again, the area under the graph is equal to the impulse. And in this case, what would it be? What would be the formula here? It's not a rectangle, so it's in fact what? Do you guys know where you are on here? Yeah. Okay. So what would it be? It's the area of the triangle, right? So it would be half the base times the height. Base times height divided by 2. In this case here, it would be 25 is the height. The base is from 0 to 1.2, and we divide by 2. Why do we divide by 2? It's a triangle. So it's going to be 25 times 0.6. I don't even have the answer here. 12. Someone do that for me. I can't do it in my head today. It's too hot to do calculations in my head. My brain will overheat. Yeah, they do, Nate. They just need to turn it on. Yes, I know. 15? And when it gets cool again, you'll be complaining. You'll say, turn the heat back on. When it gets cold? Oh, what's that? No, I meant like later next week. Yeah. 15 what, Mustafa? What's the unit for impulse? That's actually true in it's not newtons per second. It's actually Newton seconds. Newton seconds. Newtons times seconds, which, and Mustafa is correct, that's equivalent to a kilogram meter per second. Whoops. Equivalent to a kilogram meter per second, but we don't usually call it that. Okay? So the impulse here is 15 Newton seconds. All you really got to do is find the area. Remember doing this in grade 11? right? So it's just applying that same concept to a different situation. That's all it really is. Here's example number 4. Determine the impulse for each of the given graphs. You have the nice graph right there. Well, it's actually all of the area all the way down, right? So it's going to be actually what? Triangle plus rectangle, right? So it's going to be, the height here is going to be 20. The base is 1 divided by 2. That I can do in my head. 10 Newton seconds. Height is 20. Base is 1. Oh! Way to go, Cole. The rectangle. Thanks. And the next part is the triangle. Once again, the base is, well, let's do the height first because that's how I did it here. So it looks like it's going from 20 to 70. So the height is 50. I don't think we need to show that work. I think you can do that in your head. The base, once again, is 1. This is divided by 2 because it's a triangle. 25 for a total of, what am I doing? 45 Newton seconds of what? Impulse. 20 plus 25 Newton. Add the rectangle plus the triangle. Now, what do you do when it's like this? Okay, AP Psych people, what shape is that? Normal curve, right? It's a normal curve. You guys did standard deviation and all that stuff? It's a lot of fun. No? I never learned that until I actually tried to teach it in applied math. I never learned any of that stats. We need to teach way more stats in high school and way less algebra. That's my opinion. No? You hate stats, so. Oh. It gets complicated real quick. But basic stats like standard deviation and probability, I think should be taught. You're right. It does get pretty complicated pretty quick. Do they make you do it by hand, the calculations now, still? Yeah, they used to make you do all that by hand. It was a pain in the butt. Anyways, the varying force of a tennis racket on a tennis ball, this force increases, then decreases over time. So it's not a nice triangle. This is known as non-uniform changing force. This is not required. I'm not going to do this, but I'm just sort of pre-warning you what's in your future if you're taking calculus physics. Can be solved by estimating. They actually encourage you to actually just sort of like estimate the squares. Remember doing that in my grade 11 class? Right? You're counting squares. They encourage that to begin with. Or have you got to integration yet, you guys? No, it's not going to happen. When you're taking calculus next year and you talk about integration, you'll go, okay, yeah, that's what Mr. Bennett was talking about. So you would have to find out the equation for the normal curve and put it through the calculus integration process, find the area under that. I'm not going to make you do that. What do you need to be able to do? That kind of stuff. Pretty straightforward. Easy marks, don't blow it. Like I did with the half there, right? Don't blow that. Okay, there are some test questions, There are some textbook questions on page 287. Number 6, A and B, page 308, 50, and 51. And if I'm not mistaken, it's been a while because I didn't teach grade 12 last year. If I'm not mistaken, they are these ones right here. 50 and 51, yes. So what I did was I copied them out of the textbook for you to have. Okay, so you can actually draw right on there. So you can work on that sheet today, force versus time graphs. After all of this, I need, preferably by tomorrow, you should have this one here, impulse hand-in. Mine says version 3. I don't know which one you guys actually have because there's a couple versions out there. Okay. So this one here, it's got part 1, 1A and 1B, just a momentum, fat equals MAV question. And on the back side is a graph question. That's hand-in pre-test, not for marks, just a make sure you know what you're doing before the test. Okay, I'm done. I'll be quiet. Tomorrow we'll do 1D collisions. They're a lot of fun. Sure.